Good afternoon. My name is Igor Ostrovsky, and I'm a software engineer at Microsoft over in Redmond. And I'll be talking about parallelism, but I'll be talking about parallelism in .NET Framework 4 and Visual Studio 2010. Before we get started, can I see a show of hands how many of you are at least somewhat familiar with .NET? Oh, okay. So there are some people here who are somewhat familiar with .NET. How about Java? Almost everyone, or at least a large subset. So that's great because that means that hopefully a lot of you will learn something new from my talk. So the stuff that I'll talk about in the first half of the presentation are new things that are in .NET 4 and Visual Studio 2010 with respect to parallel programming. And Visual Studio 2010 and .NET Framework 4 shipped about a year and a half ago. So this is all stuff that's out there and that developers are using in production today. As for the agenda, I'll briefly talk about why parallel programming is interesting and relevant. I think that has been covered very well so far, so I'll just do a very quick recap. And then I'll talk about the .NET stuff, the managed APIs and runtime support for parallel programming in .NET 4, and the tools for debugging and profiling parallel programs in Visual Studio 2010. So why is parallel programming interesting? Well, the main reason why it is interesting is that the hardware has been shifting towards more and more cores. For a fairly long time, most of the computers were single core, and due to Moore's law, the number of transistors that is available to the hardware manufacturers to put on one integrated circuit has been doubling roughly every 2 years. And for a long time, hardware manufacturers were able to translate those extra transistors into higher clock speeds and more efficient single-threaded execution. They used deeper instruction pipelines and cache smarter and bigger caches and branch prediction and all of these tricks. But over the past few years, they started hitting problems with heat, and because of that, they decided to instead put 2 cores or 4 cores, just more cores on a single processor, instead of making a single core faster. And so now you can have these crazy machines that have 128 cores in them or more. But the problem with that is that, yes, you have these very powerful multi-core machines, but you can't just take your sequential program and run it on a multi-core machine and expect it to run faster. For a long time, if you had a sequential program, basically the hardware vendors were competing on who will make your program run fastest. And you didn't have to do anything, and you just ran your program on the next generation of hardware, and it ran faster. But now if you want to exploit these quad-core or 16-core machines, you have to write your applications in a way that they can take advantage of that. So they have to utilize multiple threads, and the multiple threads get scheduled on multiple cores, and you can take advantage of the hardware. So the first goal of my team at Microsoft is to improve the developer productivity when targeting software for these multi-core machines. We want to make it as easy as possible for as many developers as possible to write these parallel applications. And the second goal is performance. If I, as a developer, use a parallel library, I expect it to be fast. Otherwise, what's the point of using a parallel library? So now I'll get to talking about the managed APIs and runtime support that was introduced in .NET 4. these libraries and APIs are referred to as parallel extensions to .NET, although that is a bit of a legacy name because these libraries are now really a first-class part of .NET. The first point to make about parallel extensions to .NET is that they are pure .NET libraries. And what that means is that you can use them from any .NET language. For those of you that are familiar with .NET, you probably know that you can use different languages to target .NET. So you can write a .NET program in C#, Visual Basic, and a whole bunch of other languages like F#, Python, Ruby, and so on. And in all of these languages, you can use parallel extensions to .NET. Some of the languages have features that make it more convenient. For example, C# has lambda expressions, closures, extension methods, LINQ language integration. But ultimately, all of those features just boil down to manipulations of types and method calls. There are three main feature areas in parallel extensions, and I'll go over each one of those in subsequent slides. There's the task parallel library, parallel LINQ, and we have a set of thread-safe data structures and synchronization primitives. And we also have an enhanced ThreadPool in .NET 4 to make this execution more efficient, and I'll talk about that a little bit later as well. The easiest way to use task parallel library is to use it to parallelize loops. If you have a loop where every iteration is doing something expensive and different loop iterations are independent, you can just launch the different iterations in parallel on multiple threads. And if you want to parallelize loops in the task parallel library, you can use the static methods on the parallel class. So it is very simple, at least in C#. This is where the lambda expressions come in that make it very, very nice. You can very nicely convert a for loop and a for each loop into the parallel variants. I should point out that the task parallel library does not do anything to verify that that the parallelization is correct. It is up to the developer to ensure that that you don't have any race condition and that you use synchronization as necessary. I will show a quick demo of how you can use parallel loops to speed up an application. Here's a simple ray tracer, and if I run it, this is a ray tracer application that is running on a single core. And if I open Task Manager, I can see that the CPU usage is around 25%, so it is using a single core on my quad-core laptop. Now, if I stop this and click the parallel checkbox, and I run the ray tracer again, now it is running significantly smoother. The frames per second are about 4 times higher, and the CPU usage is somewhere in the 90s. And the nice thing is that if I look at the source code change between the sequential and the parallel version, the only difference is that in the sequential algorithm, I use the sequential for loop, and in the parallel algorithm, I use the parallel for loop. So ray tracing is a great algorithm for parallelization using parallel loops, because basically what you have is you have input data, so you have the pixels on the screen, and you trace array from the camera through every pixel, and then you track it how it bounces from different surfaces, and from that you calculate the color of that pixel. So because different pixels can be calculated independently and is fairly expensive to calculate it, you can easily just parallelize the computation by using a parallel loop. And that's exactly what this example does. It uses a parallel loop for the rows. So the algorithm executes in parallel with respect to the rows. Okay, I'll get back to my PowerPoint slides. Another high-level primitive in the task parallel library that is very easy to use is a parallel region. The parallel region is a set of method calls that you make in parallel. So let's say that I have methods A, B, and C, and I want to execute them in parallel because they have no dependency between them. I can just use parallel.invoke, the task parallel library method. Here is an example that demonstrates how you would do that. To make things more interesting, there's also parallel options. This also shows how you can use parallel options to tune some of the settings for parallel invoke. So here we are setting the maximum degree of parallelism to 2. That means that the parallel invoke will use at most 2 threads. And we are assigning a cancellation token so that the operation can be canceled. And then we just call parallel.invoke, pass in the parallel options, and call the 3 methods that are going to execute in parallel. Now, a lot of these kinds of high-level primitives, like parallel loops and parallel regions, you can use them to parallelize a lot of programs. But the programs have to have they have to fit the simple pattern. For more fine-grained control over parallelization, you often need to use tasks. Tasks are these fine-grained, low-overhead units, asynchronous units of work that you can construct and parallelize your workload. And I'll walk through some of that in Visual Studio to show you how you can create the tasks and manipulate them. The easiest way to create a task is to use task.factory.startNew method. And this will basically start an asynchronous unit of work that will execute somewhere on the ThreadPool. And to demonstrate that, instead of doing some work, I will just sleep for 2 seconds, and then I'll print something to console. Task T finished. Now, on the main thread, I can print something. I can print that the task T has been scheduled. Task T is scheduled. And then the main thread can wait for task T to complete. So what will we expect this code to print? What we expect is that the main method kicks off task T. Task T executes somewhere on the ThreadPool. But even before that, the scheduling is very fast because these tasks are very lightweight. So immediately we would expect to see task T is scheduled written on the console. And then 2 seconds later, we should see that the task T is finished, and then the process completes. And when I run this, that's what we see. We see task T scheduled and task T finished. Another thing that you can do with a task is you can return a value. Typically, you'd return a value that you calculated or got from a web service, but I will only return 42 for demonstration. And the type of task that returns a value is task of the type of the return value. So in this case, this task of int. And then you can get the value of the task by accessing its result property. I can say task t returned, and I can say t.result. Accessing the result property basically waits on the task to complete. And afterwards, it gives you back the computed value. This programming pattern is also called futures. So now, if I run this, we expect to see the task T finished and task T returned 42. Another thing that you can do with tasks that is often very useful is you can chain them up into continuation. A continuation is a task that will start after some task has completed. So that way you can create these directed acyclic graphs of work where you have some parallelism available. So in this case, if I want to do something after task T completes, I can say task C equals T.continue with. And I can do something else, and I'll again just sleep for 2 seconds. And then print to console that task C is finished. And actually, to make it a little bit more interesting, I'll make this a task of int as well. So the continuation will return, let's say, 100 plus t.result. And then we can, on the main thread, print what task C returned. So we can say task C returned. And we would expect that to be 142. So task T finishes after 2 seconds. 2 seconds later, task C completes, and task C returns 142. And so instead of just scheduling a continuation after a single task has completed, you can also do task.continue when all, task.factory.continue when all. And you can specify a list of tasks. You can specify a list of tasks, and then the continuation is going to execute after all of those tasks in the list have completed. And you can also do continue when any, and there are other these kinds of utility functions. So you can combine tasks into pretty complicated chains and construct. You have kind of fine-grained control over how your parallel program is going to execute. And one last thing that I'll show with tasks is how you can incorporate cancellation. Cancellation is often very important in parallel and asynchronous programs. And if I want to cancel a task or any operation, the important type is cancellation token source. Oops, cancellation token source. I create one of these cancellation token sources, and then its helper type is a cancellation token. Every cancellation token source has a cancellation token associated with it. And the way it works is that the cancellation token source has the ability to cancel an operation. So if I want to cancel some asynchronous operation, I need to have the corresponding cancellation token source. On the other hand, if I want to poll whether some operation has been canceled, I only need the cancellation token. So this is kind of a nice decoupling, so that if you have a parallel operation, you have a big parallel operation, and you only want to allow, let's say, an asynchronous network call, you want it to be able to check whether the operation has been canceled. You don't want to pass in the cancellation token source because you don't want to allow the network operation to cancel the entire big operation. You just want to allow it to poll whether cancellation has been initiated. So if I want to cancel a task, I can say cancellation token source.cancel, and then I have to associate the corresponding cancellation token with the task. And now, when I wait on this task, let's say if I try to print the result of this task, this is going to throw an exception, so I have to put into a try-catch block. And the exception that comes out is an aggregate exception, because given that this is a parallel operation, there can be multiple exceptions that happen at the same time. So we return all of them in an aggregate exception. And you can enumerate over them by accessing the inner exceptions property. So I can look at a.innerExceptions, and I can print the types of all the exceptions that are inside the inner exception. Now, when I run this, I need to print, I meant to say get type. e.getType. And we should see that task cancel exception has been thrown out of the task. Now, you may notice that I canceled the task before the task started. And it's interesting to think about what happens if I cancel a task after that task has already started running. And I can simulate that by first scheduling the task, then waiting for a little bit, and then canceling the cancellation token source. Well, the problem is that once we started running this task on some thread, we can't really cancel the task easily at the task parallel library level without potentially doing something really bad. I mean, in theory, we could abort the thread, but that is generally a really bad idea. So instead, the cancellation model requires that the developer, the one who wrote the task, is going to participate in the cancellation. So instead of, if this was some work, I would split that work up, and I would poll the cancellation token regularly. So I could say for int I could split this into 20 waits just for demonstration purposes, and I could say ct.throw if cancellation requested, so that if cancellation has occurred, we are going to cancel the task and break out of the operation. And this will be a shorter sleep time. Okay, so I'm going to go back to PowerPoint. This is what I wanted to show with tasks. Another demo that I'm not going to run is an algorithm that computes that plays reversey, and we have a parallel algorithm, and that's exactly the kind of. So when you want to play a game like reversey, you typically use this minimax algorithm that's recursive, and it does some alpha-beta pruning, and that's the kind of a problem where you can't just easily use a parallel loop or a parallel region. You need more fine-grained control over the decomposition, and that's exactly where tasks fit very well. That's exactly what you want to use. The second feature area of parallel extensions is the parallel LINQ. LINQ in .NET is the standard set of operators that you can use to query different types of data sources. So these are operators that are a lot like SQL operators. So they're going to be things like group by, order by, where, select. And you can use the same operators to query SQL data, XML data, or data that's in memory, that's linked to objects. And linked to objects is the LINQ flavor that is relevant for parallel LINQ, because parallel LINQ is basically just the multi-core version of linked to objects. Here is a simple example of a sequential linked to objects query in C#. I have an array of integers, and I'm filtering it so that I keep only those values that are divisible by 2. And if I want to parallelize this computation, because I want to run it on multiple cores, I can add as parallel. And this is all that I have to do in order to run this computation using parallel LINQ. Whether this particular computation is going to actually run faster, it tends to depend on the hardware, or it also depends a lot on what your expressions in the query are. If instead of I modulo 2 equals 0, if that was an expensive computation, you would almost certainly see significant speed up, because just by the fact that you're evaluating these expressions on multiple cores, you would get a significant benefit. In addition to using as parallel, you also have finer-grained control over how the query will execute by using these different operators, such as with degree of parallelism, that lets you control how many cores should be used to execute this query, or I should say how many threads should be used to execute this query, with cancellation that provides a token so that the query can be canceled, and so on. Parallel LINQ supports a lot of operators. There are 50 operators, 175 overloads total. So you can express a lot of interesting computations using parallel LINQ. And provided that your algorithm fits the right pattern, using parallel LINQ can be as simple as adding as parallel to your query. So it is another one of these kind of very simple, high-level programming models for multi-core. And we have a demo here. I'm going to skip that one as well in the interest of time. It is a demo where the computation is that you have data about baby names, and you want to calculate how many babies of a particular name were born in a particular year. And this computation can be nicely expressed as a LINQ query, and just simply by adding as parallel to that query, you can make it execute 3 to 4 times faster on a quad-core machine. And the last feature area in parallel extensions is the set of thread-safe data structures and synchronization primitives. This includes the thread-safe scalable collections. So these are the thread-safe versions of queue, stack, dictionary. That's basically a tree map. And these collections are optimized for multi-threaded access, and they are also thread-safe. Blocking collection is another very useful primitive. Blocking collection is basically a collection that has a limit on the size. So you can have a producer thread that inserts values into the collection, and if the collection is full, the producer is going to block. And you have a consumer or multiple consumers that are pulling values out of the collection, and if the collection is empty, the consumer threads are going to block. So the blocking collection is very useful for implementing buffers for exchanging data between different threads. I'll skip over some of these, but two that are very useful in practice are lazy and thread local. Lazy is a type that encapsulates the lazy initialization pattern. That's a very common pattern where you need to initialize some value only once, and that value might be accessed by multiple threads, and whichever thread needs the value first, that thread should initialize the value. And it's surprisingly tricky to implement this in a way that is both efficient and thread safe. So lazy of T encapsulates that pattern. And thread local of T is a container that contains, that holds a different value for every thread. So if you want to have a counter where every thread has its own value, you can just use thread local of T and access it from multiple threads, and each thread will see its own value. And the last thing that I'll mention on this slide is the cancellation support using cancellation token source and cancellation token. And I showed you how those work earlier in my TPL demo. Now, when we execute tasks in the task parallel library, we use the ThreadPool. Because these tasks are lightweight, we don't want to create a new thread every time the user schedules a task. So we use this set of worker threads that are kept around, and they execute tasks. And how the ThreadPool works has changed from .NET 3.5 to .NET 4, and I'll go over some of those changes. In .NET 3.5, if a thread created a work item, for example, if you schedule a task, that work item would go on the global queue. And then different worker threads would pull the global queue, and they would pull these work items in FIFO order and start processing them. If one of the worker threads needed to create another work item, that work item would again go on the global queue. So the global queue can become a bit of a bottleneck, especially on machines with higher core counts. The ThreadPool has two nice features in .NET 3.5. One is starvation detection. And what that means is that if you schedule work items on the ThreadPool that are very long running, the ThreadPool is going to make sure that it injects threads so that any new incoming work items are still going to get processed. In .NET 3.5, the logic is something like, if there are work items on the global queue, but none have been removed in half a second, the ThreadPool is going to inject a thread. So that way the system doesn't get into starvation. And another feature is that the ThreadPool shrinks. So if there are threads that are not doing anything, the ThreadPool will eventually retire them. In .NET 4, the kind of obvious difference that you can see in the diagram is that now every worker thread has its own work stealing queue. So if you schedule a task, initially all of the tasks go as work items on the global queue. Then these work items get picked up by the worker threads, again in FIFO order. However, if one of the workers needs to schedule additional work items, those work items are going to go on that worker's local queue. And then if the worker completes its own work item, it can get more work items very efficiently without having to go to the global queue. So that reduces the contention on the global queue. If another worker completes its work item and its local work stealing queue is empty, it will try to steal a work item from one of the other workers whose global queue is not empty. And just like in .NET 3.5, the ThreadPool provides starvation detection and idle thread retirement, but it also has this nice hill climbing algorithm. So basically what the ThreadPool in .NET 4 does is it tries to optimize the number of threads to get the best possible throughput. So it measures how many work items are completing per second, and it tries to add a thread, and it observes how the number of work items that are completing has changed. And if it has improved, then it will try adding more threads. And if it hasn't improved, then it might try removing a thread. And based on that, this is the kind of hill climbing algorithm that it uses to get the thread pool to have the optimal number of threads for ideal throughput. So far I talked about the managed APIs and runtime support in .NET 4 for parallelism. Now I'll quickly talk about some of the new tools in Visual Studio 2010 for debugging and profiling concurrent programs. The new debugging support in Visual Studio 2010 includes the Parallel Tasks window and Parallel Stacks window. The Parallel Tasks window is very similar to the Threads window for those of you who happen to be familiar with Visual Studio 2010, but it displays tasks. So you can see what's the status of your tasks, which ones are scheduled, which ones are running, which ones are waiting. You can see which threads are executing your tasks, and you can also see the call stacks for different tasks. The Parallel Stacks window provides a very interesting view on the call stacks in your application. When you're doing parallel programming, what often happens is that the call stacks have a big common part. So let's say that you have 16 threads or tasks. What often is the case is that the bottom part of the call stack is going to look the same. So they are all probably might be in some ThreadPool worker method, and then on top of it is going to be the parallel library code, and then afterwards you will see some of your code, and then the call stacks are only going to differ at the top. So the Parallel Stacks window gives you this nice visualization so that you can see all the call stacks grouped together without having to see 16 separate call stacks. You might just see one big common part and then kind of leaves at the top. Concurrency Visualizer is another new tool for parallel programming in Visual Studio 2010. And you can start it just by going to Analyze, Launch Performance Wizard, and then you select Concurrency, visualize the behavior of a multi-threaded application. And the Concurrency Visualizer provides three views. The first view is the CPU utilization view. And it basically shows you how much of the CPU your application used over time. So after this profiling session, you can see the green area is how much of the 4 cores this application has been using. The yellow area at the top, those are other processes that have been running on the machine. And the little bits of red area, those are the system processes. Probably the most frequently used Concurrency Visualizer view is the Threads view. Threads view shows you this horizontal lane for every thread in your application, and you have different ways of filtering those threads and kind of getting at different types of data. The green area, that's where your thread was executing. The red area is where it was blocked on synchronization. And then there are more states, so purple is I/O and so on. And you can hover your mouse over some of the green areas, and you can see call stacks. And you can click on the red areas. Those are the times when your thread was waiting in synchronization. And you can see both the call stack that initiated the wait, and you can also see the call stack that unblocked that wait. So this gives you a nice tool for understanding how your threads kind of were waiting on each other and how they're making progress together. And the last view in Concurrency Visualizer is the cores view that shows you the cores on your machine as these horizontal lanes, and different threads are shown as different colors. And this can help you analyze some types of issues such as thread migration between cores. And also you can see how, it can help also understand how your application has been utilizing the cores on the machine. Okay, so that was the first part of my presentation. And now I'll talk about some of the future things that we are working on. The disclaimer for this part is that this is future work, so this is stuff that we are working on. Either everything or almost everything I'll show is available in technology preview form, so this stuff that I'll show can be downloaded, but it may perhaps never ship, although we are definitely working on getting there, but there are right now no guarantees. And I'll talk about two new technologies. One is Visual Studio Async, and the other one is TPL Dataflow. Visual Studio Async is a pretty broad cooperation at Microsoft in order to make asynchronous programming easier and more accessible. Just out of curiosity, how many of you have tried writing a smartphone application for like iPhone or Android? Okay, not that many. But for a lot of smartphone applications or these types of connected applications, the problem that you need to solve is that you have some user interface, the user clicks a button, and as a result of that, the button might be find me restaurants that are close to me. And then this needs to fire off request to some web server. And the problem is that the application needs to keep doing stuff. It cannot wait until the web server responds, because otherwise the user interface would look like what the slide shows. It would just be frozen. The user cannot do anything, cannot cancel the application, cannot cancel the request. So that's a very bad user experience. So this type of asynchronous programming is very, very common. And Visual Studio Async aims to make it easier and more productive. So let's take a look at what that might look like. If I have a synchronous method, foo, that accepts some parameters and returns a value, if I call that method, what happens is that my current thread is not going to get control back until this synchronous method has completed and it has produced its result. However, that might not, if I want to execute this method in an asynchronous way, the pattern that has been in .NET since the first version is this asynchronous programming model pattern. And if I want to expose foo as an asynchronous method, I would need to provide two methods. I would provide a begin method and a foo method. So the user who wants to call my asynchronous method would call begin foo, and in addition to the argument list, they would provide a callback and state to associate with the asynchronous operation. And then once they get the callback back that the asynchronous operation has completed, then they call the end method. And from the end method will either throw an exception if the asynchronous operation failed, or it returns the result. So you definitely can expose asynchronous operations this way, but it gets pretty complicated. A second pattern that is used broadly in .NET is the event-based asynchronous pattern. And the way that works is, if I want to call an asynchronous method, I will first register an event handler, and that event handler is going to fire when the asynchronous operation completes, and then I call the foo async method that is going to kick off the asynchronous operation and immediately return. Now let's take a look at a simple synchronous operation. Here is an operation that copies all data from one stream to another stream. It just uses a buffer and kind of one chunk at a time. It copies all the bytes from source stream to destination stream. An expertly written asynchronous version of that code using the asynchronous programming model is on the slide on the right. So there's a lot of code there. Basically, you always have to make sure that your method returns quickly, but it also needs to schedule. Needs to make sure that the asynchronous operation is always running, and it needs to make sure that the exceptions will get reported, So writing the code this way is quite challenging and not very convenient. And also using the asynchronous method that exposes the begin and end methods is not that convenient. But it certainly can be done. That's how people have been doing asynchronous programming ever since .NET has been around. But Visual Studio Async aims to make this a lot easier. At the bottom of the slide now is the asynchronous method as implemented using Visual Studio Async. And I'll highlight what's different at the bottom sample. We have these new keywords. These are new C# keywords that the C# compiler recognizes, async and await. And we have a new naming convention where asynchronous methods end with async. And as the final difference, the asynchronous method returns task instead of returning void. So this is the task from task parallel library that is used here. So to summarize, the new concepts for Visual Studio Async are the async and await keywords. The async keyword tells the compiler that this is not an ordinary method. This is a method that needs to be rewritten so that it runs asynchronously, so it needs to be broken up into this state machine. And an await keyword tells the compiler that the rest of if you await a particular task, it tells the compiler that the rest of this method needs to be scheduled as a continuation after the task, and the method needs to return right away. The framework provides various classes that the compiler uses in order to implement all this functionality. And the task and task of tResult types are used to represent the ongoing operations. So a task can represent either long-running background work, or it can represent I/O operations, or network operations, or kind of other asynchronous operations. And there are also new APIs in the task parallel library that fit nicely with Visual Studio Async and make it more convenient to use it. We added task.whenAll and whenAny operations that make it you can construct tasks that complete after a particular set of tasks, either all of them or any of them have completed. There's task.delay that lets you construct a task that automatically completes after a certain time period. I'll show how you can use that in just a moment. And a few additional utilities that are nicely fit with this asynchronous programming style. So hopefully in .NET the plan is that we'll be able to obsolete the two previous patterns, the asynchronous programming model and the event-based asynchronous programming model, and replace them with the task-based asynchronous pattern, where you just have a method that is named ending with async, and it returns a task of tResult. And as a part of this effort, it's important to convert all the existing asynchronous APIs in .NET to use this task-based asynchronous pattern. So all of the I/O, or at least much of the I/O and the network accesses, the WCF, which is the kind of like RPC in .NET, all of those APIs we are hoping to get converted to this task-based asynchronous pattern, so that is the way that you can do asynchronous programming in .NET. Okay, I will show a quick demo of how you can use the asynchronous programming. Here I'm using the Visual Studio Async CTP. So that, again, is something that you can download. And the application that I'll show is a simple countdown application. So the user interface just looks like, well, what will be shown here in a minute. I have a button and I have a label. And when I click the start button, I want to change the label to count down once every second. I have an implementation here that I have a button click handler that decrements, that runs in a loop 11 times, and each time it decrements the iteration variable, and the thread will sleep for 1 second. Now, does anyone see what will be wrong with this code? Yes. Yes, exactly. The click event handler is getting called on the user interface thread. So when I loop here for 10 seconds, I'm doing something expensive. I completely block the user interface thread. So the user interface is not going to get updated. It won't even show the updated counter, and it will just freeze. So if I show this, if I run this, if I hit start, nothing is happening. I can't even move the window. Just the application completely freezes for 10 seconds because I have just kept the UI thread busy for 10 seconds. And then eventually, after 10 seconds, the UI thread gets control back. If I want to fix this application, I need to write the click handler in an asynchronous fashion. So I can change the button onClick method to be an async method. And that instead of sleeping for 1 second, I am going to await some task. And the task that I can await is just a task that will complete in 1 second. And the way to construct such task is using this task exe.delay 1000 method. And now if I run this, I can see the countdown and the user interface works. If I had a cancel button, I could easily cancel the operation and so on. So this was a very easy way to convert a synchronous method to an asynchronous method. And basically the way the asynchronous method works is that the first time it is called, I set to 10, the label is updated in the user interface, and then the method has to remember everything that has to be done. So it has to schedule a continuation after this task that has been returned from task exe.delay, and then the method immediately returns. And then eventually the continuation comes back, and it will again go back on the UI thread because we automatically capture the synchronization context. And again, the I is decremented to 9, the label is updated, and again, the continuation is scheduled, and the method again returns quickly. So the UI thread gets to maintain control. A second new thing that is coming up in the future in .NET is the task parallel library Dataflow. In the programming models that I have described so far, in the parallel loops and parallel regions and parallel LINQ queries, the way you can think of them working is you have some data and you invoke a parallel operation over them. The kind of different way of representing a computation is where you first set up a computation and then data comes in, and that data goes through the computation. And that's what the TPL Dataflow is about. In TPL Dataflow, you construct computation out of blocks that are linked together and pass messages to each other. And this network then performs your desired computation. There has been a lot of work in these kinds of data flow networks, specifically at Microsoft. We have shipped the asynchronous agent library in Visual Studio, in Visual C++ 2010. Microsoft Robotics team has built the CCR library, and we've had an Axum incubation project that was about these data flow networks but integrated into a programming language. And the TPL Dataflow takes all of the things that have been learned and puts all of these concepts behind a production quality .NET API. A kind of hello world example for data flow is an example where you just have a single action block. So I created an action block here that calls some process method for every message that it receives. And then you can, in a loop, you can pump messages into the block. You can call post and push different values into the block. And basically what happens was, as you post the value into the block buffers all the messages that it has received, and it will start a task in order to start processing these messages. And as more messages arrive, the task continues processing them, and eventually, if the queue becomes empty, the task goes away. And then again, if another message arrives, the task will come back and process more messages, and then again go away. There are different types of blocks that you can put together in order to construct these data flow networks. There's buffer block that buffers up elements, write once block that accepts exactly one element, broadcast block that broadcasts a message to all of its linked blocks, action block that performs a message for every message, that performs an action for every message that it receives, a transform block that evaluates a function for every message and generates a new message, a transform many block that receives a message and generates multiple messages, and so on. There's the batch block that groups multiple values into one array, join block that creates a tuple out of multiple messages that it has received, batch join block, and so on. And so you can construct some very useful networks out of these and construct different types of parallel programs compared to what you would do with task parallel library or parallel LINQ. So I think we are just about out of time. You can take a look, if you want more information about the Microsoft concurrency libraries, you can go to the Parallel Programming Dev Center at msdn.microsoft.com/concurrency. I don't think you don't actually need the E and -US part. Thank you. I think that we'll have a message as to what's next.
Questions?
Any questions?
Well, let's thank the speaker.